Welcome to lecture number 37 of the course on nonlinear structural analysis, theory and applications. So, let us see what we have done in the previous lecture. So, in the previous lecture we have discussed some examples again using elastic perfectly plastic material behavior. But if you recall, in lecture number 17 we have discussed that material strain hardens, right, and there are three different types of hardening rules that we discussed: isotropic hardening, kinematic hardening and independent hardening. But that discussion was for uniaxial loading only. Okay? So, for uniaxial material models. Now, the plasticity theory that we have discussed can be easily extended to incorporate the effect of strain hardening. Okay? Again, conceptually we will be looking at the hardening rules. Okay? We will not get into the mathematical derivations in the interest of time, and also we will be using OpenSys for doing the computation. So, therefore, it is not necessary to get into the mathematical theories of plasticity, okay? And we will also solve some examples. So, as I said, we have isotropic hardening, kinematic hardening and independent, which I am not going to discuss because I cannot really demonstrate, and whatever I discussed earlier for uniaxial remains basically valid. And then I will talk about some issues with linear isotropic and kinematic hardening rules. Okay. So, let us recall that for elastic perfectly plastic material behavior, the yield function or the surface, yield function means when I write F sigma, okay, or the surface means when we show it geometrically, this remains unchanged. Okay. For strain hardening materials, yield function progressively changes in shape, size and position. In reality, a material does all three: the yield surface changes in shape, size as well as in position. It can move. The hydrostatic axis need not be the axis of the cylinder. The cylinder can translate, but the axis should remain parallel to the hydrostatic axis. Okay. So, a hardening rule defines how yield function changes in size and position. Shape is a complicated thing, we are not getting into that. Okay. Typically, we will talk about the changes in size and position. Okay. There are two widely used hardening rules. One is called the isotropic hardening rule of Hill, which was developed in 1950, and the kinematic hardening rule of Prager, which was developed in 1956. Okay. So, what is the idea? Again, let us go back to the EPP first. So, like I said, the yield surface does not change for elastic perfectly plastic material. So, which is shown in this figure, which I have taken from this book by Neto et al. Okay. So, this hatch thing is indicating that the yield surface is glued to the deviatoric stress space. It cannot move, it cannot go anywhere, it cannot change in shape and size. So, that means if I now take a material and apply uniaxial loading, let us say in the sigma 3 direction. So, what I will do? I will move along this path. So, that is what I am showing: stress versus strain response. We are moving along this path. Okay. And I have already shown this using OpenSys, but where I drew the yield surface in the principal stress space sigma 1, sigma 2, but now here I am showing it on the deviatoric stress space. Remember, some authors call the deviatoric plane that is passing through the origin a pi plane, but some author call all the deviatoric planes pi plane. So, that is what it is shown here, it is called pi plane, okay, which is basically projection of the von Mises cylinder when you are looking from the hydrostatic axis. So, what happens? Well, you start here, you go along this. So, you go, the stress state reaches the yield surface and it remains there if you continue loading plastically, right. If you unload, then you move in this direction. How does it move here? Well, let me show you. We went like so, right. Now, when we are unloading, we are going in this direction. So, what is happening here? So, now we will use a different color. So, we are going in this direction and the material yields again at this point. So, from here to here, this behavior is elastic, which is captured by that, and the yield surface is not going anywhere, not changing in size. That means, the radius of the yield surface remains the same. Okay. This is elastic perfectly plastic material behavior. Now, when we talk about isotropic hardening, what it means? It means that it corresponds to expansion of yield surface with no change in shape and no shift in origin. That means my circle in the deviatory plane remains a circle, the origin remains at this point, but the radius of the circle now increases. Okay? That is what is isotropic hardening means, the expansion of the yield surface without changing its shape and without changing the origin. So, that means initially let us say this is my yield surface in the deviatory plane corresponding to sigma y. So, often we call it the initial yield surface denoted by y, and as you keep loading the material, what happens, let us say we are going in this direction, this is my stress path. When you reach the yield surface, then the yield surface starts to grow and your yield strength increases. Okay? So, that is what is shown here. This is called the hardened surface. Okay? This can keep growing depending on the nature of the hardening rule. Okay? So, let me show you another example. So, let us say this is my initial yield surface, right, and on the right I am showing you the stress versus strain. Let us say we are loading in the sigma 3 direction uniaxial state of stress. Okay. So, you move in this direction, you reach this point. So, here in the stress strain you reach here. The moment the point reaches the yield surface, then it starts to grow. Okay. Now, that nature of growth of the yield surface can depend linearly on the plastic strain, non-linearly, we are not getting into those discussion, but it can be linear as well as non-linear. So, when that growth is non-linear, then from here to here you can get a non-linear relationship. So, this is growing, this yield surface is growing, and let us say at some point it is this, right. So, you go up to that point. Right. Now, depending on what kind of nonlinear isotropic hardening is used. Okay. So, for example, I will show you the isotropic hardening where this is kind of fixed, right. So, it can go only up to that, it cannot go past that point, right. Now, when you have gone there, okay, then what happens? You are unloading. So, if you unload, what happens? How long the material will behave elastically? Well, this is now the current yield surface. You were here. So, if you unload, you go in this direction and the material remains elastic unless it touches the yield surface again. So, that means it has to go all the way to this point which corresponds to that, right. So, material behavior is linear elastic up to that. So, what is this value and what is that value? Well, they must be equal. If I call this is sigma A, okay, this must be negative of sigma A, because what is this? This is the radius of the yield surface. So, it is not changing. So, therefore, whatever was the value here, this is the same value, and then again the moment you touch here, it can expand. Okay. So, in this case this may not be the ultimate surface. So, it can still grow in size. So, therefore, it is going like that. Okay. So, I will show you an example. So, now in the open phase, the J2 plasticity model that we have used earlier features only isotropic hardening, it does not have kinematic hardening, and the parameters as we have seen earlier, we have the bulk modulus, we have the shear modulus, and then we have sigma 0 and sigma infinity. So, sigma 0 is the initial yield stress which we have been using so far, we are using 300, and sigma infinity, the final saturation yield stress, I always kept it equal to sigma 0. Okay, because we are discussing EPP material behavior. Now, what I will do? I will set it higher than the sigma 0. Okay, and then there are two parameters, delta I kept it something, does not matter as long as these two are equal. Okay, and H I said I am using a small value, so that there is no isotropic hardening. I used H is equal to 1, but now we will be using all these three carefully to incorporate isotropic hardening. So, let us understand the meaning of this parameter. So, this H is actually for uniaxial loading the plastic modulus which we called E sub p in lecture number 16 and 17. If you go back to lecture number 16 and 17, you will see what is the plastic modulus. So, for uniaxial response, the plastic modulus means if you have sigma versus epsilon, let us say this is your stress strain response, right. So, I can remove the elastic part and draw the stress versus plastic strain, which will be something like that. At any point here, the tangent to this is actually the plastic modulus E sub p. Okay? So, this is what is my H. Okay? Now, note that linear hardening means there is no limit on the growth of the yield surface. The yield surface can grow infinitely. Okay? On the other hand, if we use exponential hardening, which is a nonlinear hardening, then the yield surface has a limit. The maximum yield stress that you can achieve is sigma infinity, which is what this variable is, okay, that you are going to give as an input as an user. Okay? And the rate of nonlinear hardening is controlled by this parameter delta. Okay? So, provided you set this sigma infinity is greater than sigma 0. In my previous example, I set them equal and there was a non-zero value of delta which did not do anything because sigma infinity was set equal to sigma 0. Now, if we do this, then delta means a higher value of delta means you will approach rapidly this sigma infinity. A lower value means the rate is slower and delta is equal to 0 means there is no isotropic hardening. So, this parameter is for nonlinear isotropic hardening and this is for linear isotropic hardening. Okay? So, now let us revisit the example that we did in lecture number 17. If you go back and take a look, you will see that we have an elastic linear work hardening plastic which we often call bilinear plastic material and the stress versus strain relationship was given like this. Okay? So, this is my plastic strain. Okay? And then we said in lecture 17 that sigma y0, that is sigma 0 in OpenSys notation 207 MPa, E is 207 GPa and this M is this quantity 25.9 GPa. And if a material sample is given this strain cycle, sketch the sigma epsilon curve for isotropic hardening, kinematic hardening and independent hardening. We solved this example in lecture number 17. Please go ahead and revisit. So, I will just give you the final answer. So, what we did, first step is determine what is the plastic modulus. What is the plastic modulus? Well, if I go back, if this is my EP, then EP is nothing but del sigma del epsilon p, or for uniaxial I will simply write d sigma d epsilon p. Okay? So, that means here if I differentiate and the sigma expression with epsilon p, this is what I get, which is nothing but my m. So, I am differentiating this equation with epsilon p. So, I get m, which is my plastic modulus, okay, 25,900 MPa, right. And then once I get EP, I can get the tangent modulus, which is again that was discussed previously, Et is equal to E into EP divided by E plus EP, where E is the elastic modulus and this is the plastic modulus, right. With that, we are ready to draw the stress strain. So, the material yields here at 207 MPa, this is my yield strain. After that, this slope is tangent modulus, which is this. I know that, I can calculate this and we take it to 0.007. So, we are at point A. For isotropic hardening, when you unload the material, you unload complete here, then reload in compression and it yields here. What is the stress? Minus 345, because you have gone up to 345 in tension, right. And then from here you again go like so. So, this we discussed in detail in lecture number 17. My objective now is to reproduce this result using OpenSys. Okay. So, we have to set the nonlinear or exponential hardening parameter delta equal to 0, then we can get this using linear hardening. So, this is that example. I am taking again a single quadrilateral element, these are the 4 nodes and the boundary condition x is node 1 is pinned and node 4 is a roller. So, I will show you. So, this is the element and boundary condition. I will be applying horizontal force at node 2 and 3 and perform a displacement control analysis. Let me look at my material parameters. So, E is equal to 207 GPa. Nu is 0.3, so I am calculating K and G, sigma 0 is 207 and sigma infinity is equal to sigma 0 because I don't want to consider the exponential hardening. So, sigma infinity is set to sigma 0 and delta no matter whatever value you can give, no issue. I am considering only linear isotropic hardening and that plastic modulus is 25,900. Okay. So, then the rest is something we have explained earlier. Okay. I am doing a displacement control analysis and let me show you the final result. Okay. So, these green dots are the solution that we have done in lecture number 17 by hand calculation and then the red is what you get from OpenSys. So, it matches exactly. So, now you know what OpenSys is doing when you put the non-zero value of H, that is the linear hardening modulus. Okay. And you can plot the stress histories. So, I am plotting the stress histories just to show that this point the value of stress is equal to that point as we have explained earlier and this value is equal to that value because of isotropic hardening. Okay. This is my initial yield surface, okay, which is the von Mises ellipse in the sigma 1 sigma 2 space. Now, what has happened? You started here, in this case the first 0 0 is not captured, you started here then went like so, okay, and the material yielded here, right. Then what should happen? The yield surface will grow in size, which I cannot show because I just do not have the all the variables from OpenSys as an output. Okay. Otherwise, I could have drawn how the yield surface is growing. Okay. So, eventually this yield surface, this point will stay on the yield surface, the surface will grow, okay, and the yield surface will actually come here, it is going to be a bigger ellipse like that, right, and then when it unloads it goes like that and comes to this point, right, and then you cycle here because this is purely uniaxial. Okay. This is the load I am plotting at the last step, which you can take a look. Now, let me go to the nonlinear case where I will be setting H is equal to 0, no linear hardening term, and in this case that means I have an ultimate yield surface which corresponds to sigma infinity, okay, and we have to take sigma infinity greater than sigma 0, okay, and we will take different values of delta and show you what is the effect. Okay. Let me go to the example. So, before I actually use this displacement history which was used in the previous example, let me first take a simpler one. So, let me take this one, okay, and run this analysis and show you what isotropic, what nonlinear isotropic hardening means. So, it means this is nonlinear as I was explaining earlier. If you use a linear isotropic hardening, then this will be a straight line. For nonlinear, this is actually nonlinear. Okay. Now, let me go back and take the same strain history. Let us first discuss what are the values we have taken. So, I have taken sigma 0 is equal to 207, sigma infinity is 400. That means, my stress can never exceed 400 MPa, that is sigma infinity. Delta I have taken 100 and H is set to 0. So, let me run this and show you the stress strain response. Okay. So, as you can see from here it has gone up to this, it is not linear, okay, it is non-linear. So, it has gone here. Now, what is this value here? Well, this must be equal to that, okay, and then again this is non-linear, whatever number stress you have here must be the same here, and then this is again non-linear. Okay. So, the growth is kind of bounded by the ultimate surface and the rate is controlled by the parameter delta. Let me increase the value of delta and see what happens. Before we get there, let me show you what is happening in the stress path. So, this is my initial yield surface, right, which is growing. Like I said, I do not know exactly how it is growing, that means I do not have the data from the OpenSys, hence I am just showing you the initial and the final one. Okay. So, that means the stress point will always be on the yield surface the moment it yields. Okay. So, this yield surface basically is here. The objective behind plotting this is to show that for exponential hardening this point can never go beyond or go outside this black ultimate yield surface. Okay. So, let us increase the value of delta. So, if I increase the value of delta, make it 1000, right, then see what happens. Look at the stress strain response. Now, you see earlier it was going like that, now it is going like so, right, and reaching the 400 very quickly, right. So, it has gone here and then here this is already 400. So, you do not see anything, any hardening here, because you have already reached the maximum yield surface, the biggest yield surface or the ultimate surface. So, this response is EPP, elastic perfectly plastic. So, then after this point, whatever cycle you do, the response is going to be elastic perfectly plastic, because you have reached the outermost yield surface. Okay. So, let me show you that. Here it is. So, you have gone here, here, you cycled and then finally stopped here. Okay. You are not going past or going outside this outer yield surface, right. Okay. Now, let me take non-zero value of H and non-zero value of delta and show you what happens. Okay. So, let me make that delta is equal to 100 and then this is, let us say I am making 1000, right. So, we will get a combination of linear and nonlinear isotropic hardening, right. So, this is how it is happening. Now, will it remain within the ultimate? The answer is no, because you have added a linear part. Okay. So, as you can see, well, this is not going beyond. Let me increase the stress. So, let me add here another cycle. I missed the comma. So, now still not going. Okay. So, let me go ahead and change this hardening to 2000. So, the stress strain response is like that. Well, it is not exceeding 400 yet. Okay. So, let me make it even further. Let us say the same number that I had, 2950. Okay. Then what will happen? Now, the stress strain response, you see it has exceeded 400. Because of the linear term, now sigma infinity cannot be respected, because I have added a linear term. Okay. So, that means it will keep on growing. See, this is now outside this black surface which correspond to sigma infinity. Do not misinterpret it. Actually, this point is on the yield surface which I am not able to draw, because I do not have access to all the data. Okay. So, if you have a linear term, the yield surface will keep on growing for isotropic hardening, right. Now, let us talk about kinematic hardening. Unfortunately, I will not be able to do an example of kinematic hardening, because OpenSys J2 plasticity material model does not have kinematic hardening. Nevertheless, let us understand conceptually what it means. So, kinematic hardening means it corresponds to translation of the yield surface with no change in size and shape. So, let us say this is my initial yield surface which is centered at the origin. Okay. Now, the moment the state of stress reaches the yield surface, then the yield surface translate in the deviatory stress space. Okay. So, as shown here, the diameter remains the same and it just translates. Okay. So, this is called hardened surface. If I show you in a similar manner, let us say this is my initial yield surface and this beta is basically the back stress vector which you are not getting into. Okay. So, let us say you started loading from here, that means here, okay, sigma 3 is the direction of loading. So, you go, this is linear elastic, because you are going and reaching the yield surface. The moment you reach the yield surface, now the yield surface will translate in the deviatory plane, okay, and the point remains and the yield surface will like so eventually comes to this point, right. This translation again can be linear, can be non-linear, right. So, if it is linear, then you will get a straight line here. If it is non-linear, then it is like this, right. Now, you have reached this point, okay, and you are unloading. So, if you unload, what should happen? Until this point goes down and touches the yield surface which is now this, the material will remain linear elastic, and that is what is happening from here to here up to this point. Now, this is corresponding to the same yield surface which has translated. Okay. So, the material yields at this point, right. And again, the moment it reaches the yield surface, this yield surface will move in the other direction and it goes like that, right. So, what is happening, since we have taken the material in tension beyond its initial yield strength of, let us say, which we called earlier sigma y0, when we unloaded and loaded it in compression, it yielded at a much smaller yield stress, right. And what is this called? This is called the Bossinger effect. So, the kinematic hardening, as we have pointed out earlier also, actually captures the Bossinger effect. Okay. So, this is how it is done, and once more, if this is linear, you have a linear kinematic hardening. Okay. So, now let us talk about some issues with linear isotropic and linear kinematic hardening rules. Let us consider a bilinear stress strain relationship. When I say bilinear, means I am actually talking about linear isotropic and linear kinematic hardening. And I want to consider constant range of stress between sigma A and sigma B. I have two stress, I have got a material, I am going to apply uniaxial stress, the material behavior is assumed to be bilinear elastic. I will apply cyclic loading in such a manner that my stress is between sigma A and sigma B. So, it is called constant stress cycling. And then I will do another case where I will cycle the material between two constant strain epsilon A and epsilon B and see what kind of response I get. So, this is coming out of this report, chapter 2. Okay. So, what is constant stress cycling? So, let us say I have sigma epsilon, okay, and I am considering magnitude of sigma A, the stress in the positive direction is greater than sigma B, just for the purpose of discussion. Okay. So, if I use isotropic hardening, what happens? Material goes like this and yields here. So, let us say this is my sigma 0, material yields there. Now, it strain hardens, goes along this and reaches sigma A, which is the stress I want to take it to. Okay. I have taken it there. Now, when I unload, right, this is unloading is completed at this point, I load it in compression, right, and I am saying sigma B in magnitude is smaller than sigma A. So, what should happen? I have come to this point. Now, I want to cycle it back to sigma A, because I want to cycle between two stress sigma A and sigma B. So, if I cycle from here back, what happens? I will go along this path, because the material has not yielded in compression, because sigma B is smaller than sigma A. That means, when I go back from here, it will go like so, and you come here, you come down. So, it will be predicting elastic loading after this first cycle, complete elastic behavior. That is what isotropic or linear isotropic hardening will do. Okay. On the other hand, what kinematic hardening does, let us see. So, let us say you start here, you go here and reach the same sigma 0, and then there is the strain hardening, okay, and you go to sigma A, right, and then you unload, right. So, because of the kinematic hardening, what will happen? It will yield earlier at what point? Well, this is total sigma y. So, if I use the same notation, this is basically sigma y, this is basically sigma y. Okay. So, from here to here is 2 sigma, it will yield here, and then it will strain harden and go to sigma b, right. And from this point, we are reversing, because we wanted to cycle it between sigma A and sigma B. So, it will go like this, and again yield here will go like so. So, it is predicting a stable hysteretic behavior. Depending on the value of sigma A and sigma B, this loop will look slightly different, but it is going to predict a stable hysteresis loop under constant stress cycling, whereas isotropic hardening is predicting completely elastic response in constant stress cycling after the initial loading. Okay? That is a big difference. So, what I said is written here. This predicts complete elastic cycling after first loading, and this predicts cycling around a stable hysteresis loop, the same result which I showed in the previous slide. Now, let me talk about the constant strain cycling. So, on the left I have isotropic hardening, on the right I have kinematic hardening. So, let us say Again, linear isotropic hardening, that we should remember. So, we are starting here and the material yields, and then the material is strain hardening. I take it to this strain epsilon B, and on the left side I have epsilon A. I will cycle between these two strain. So, I go to epsilon A, then unload. What should happen? Well, it should go all the way until you reach the same stress. So, if I call this is my sigma A, then this point in magnitude is also sigma A, because it is isotropic hardening. Then what will happen? Well, you will go like so and you reach epsilon B. So, you are at this point, right. So, let me mark this stress here is sigma B, the magnitude, right. Then when you reload, then when you unload in compression, reload in tension, you go to this point. What is that value? That value is equal to sigma B, right. And then you go like so. Here you reach epsilon A. What is this value? Let us say this is sigma C. I am just writing the magnitude. Come back from here all the way up to what point? Well, up to sigma C. Let us say this is here sigma C, right. Then what will happen? You will go along this, and then from there you will go like so. So, what is happening? The hysteresis loop is collapsing. Okay? This is called sec down. This is what is linear isotropic hardening predicting. After a few cycles, the hysteretic response is becoming a straight line, linear elastic response, which is called a sec down. On the other hand, the kinematic hardening, what it is showing, that you go from here, okay, you go to this strain, right. Then when you take it back, it must yield early, because this must remain your 2 sigma y, okay. And then you go this path and again like so. So, it is again able to predict a stable hysteresis loop, okay. That is the difference. So, in summary, the isotropic rule, initially you get inelastic cycling, but then it sec down to completely elastic cycling after a number of cycle, provided you have linear isotropic hardening. Does not happen so for exponential isotropic hardening, which I shall show. And kinematic hardening again produces a stable hysteresis loop. So, let me show you this in OpenSys. Well, you can take a look at the OpenSys example, because I have all the parameters. The OpenSys example is shared with you. So, I have taken sigma 0 is equal to 207 MPa, sigma infinity is 207 MPa, made them equal because I want to consider only linear isotropic hardening here. So, I have the same number 25.9 GPa, delta is set to 0. So, this is linear. As you can see, where did we start? It started here, it is going following this path, right. So, you are able to see how it is completely, after few cycle, it is predicting an elastic response. This is called sec down, okay, for linear isotropic hardening. If you do nonlinear isotropic hardening, well, this does not happen. This is what is I am doing here. Now, sigma 0 is 207, sigma infinity I set it to 300 MPa, and all other parameters remain the same. H is set to 0, there is no linear term. If you include linear term, you will be getting that behavior, okay. And delta I have taken 10, okay. You can change the number. So, you can see what is the behavior, okay. So, it is not a stable hysteretic loop, just like kinematic hardening, but you do get some hysteretic response, unlike this case, okay. Should we be concerned about this? Okay, let us discuss. So, neither of the two rules predicts behavior which agrees exactly with experimental observation. Linear isotropic rule is grossly incorrect in predicting elastic behavior for constant stress cycling. Okay. Kinematic rule is generally incorrect in predicting stable hysteresis loops, but weakness of kinematic hardening rule is less serious than those of isotropic hardening rule. Let us look at some more experimental data. So, this is a data coming out of this report. actually they have taken it from another reference. Okay. So, this is for mild steel ASTM A106. This is showing constant strain cycling. What do you see? You see kind of a stable hysteretic loop, and kinematic hardening was able to produce that for constant strain cycling, right. Now, this is another data which similar data I have shown you earlier. Okay. We are not doing constant stress cycling, but what is important here, you see after the first cycle you can see pronounced Bossinger effect, the material is probably yielding here. Okay. So, it is yielding here, and then in the subsequent cycle you can see that there is a growth of the yield surface, right. So, it is basically showing both kinematic and isotropic hardening. Neither of this effect can be captured by pure kinematic hardening rule. Okay. So, you need both isotropic and kinematic. So, there are rules, there are more complicated models, we are not going there, going to discuss those in the interest of time. Okay. Before I finish, one point, should we worry about constant strain cycling, constant stress cycling? As far as earthquake related problems are concerned, where the loading is primarily transient loading, we need not worry so much about the constant strain versus constant stress cycling. Nevertheless, we should understand the limitations of the two model, linear isotropic and linear kinematic hardening rules. Okay. And in reality, a material shows a combination of the two, as I have shown here. Okay. Loading unloading criteria is one of the another ingredient of plasticity theory, which is basically a rule that enables continuing plastic flow to be distinguished from elastic unloading for any current plastic state and specifies 10 increment. We need not worry about it, but because this is a main ingredient of plasticity theory, I thought of mentioning. So, it is basically saying when you reach the yield surface, this rule will tell you whether from that point onward it will be a plastic flow or you are going to unload. So, that is what is determined by this loading unloading criterion. Okay. I am not getting into the mathematics like I said earlier. Okay. So, let us summarize what we have done in this lecture. We have discussed the concept of hardening. We have talked about isotropic hardening and did a couple of examples. We have understood the J2 plasticity material model in OpenSeas, which has two hardening parameters, H and delta. Okay. H is for linear isotropic hardening and delta is for exponential isotropic hardening, for which you have to also use the value of the ultimate yield stress, which is sigma infinity. Okay. Then we have discussed the kinematic hardening rule, right, and we have also discussed the limitation of the linear isotropic and linear kinematic hardening rules, right. Now, next what we want to do, we shall try to see how the concept of plasticity theory can be extended to apply to PM interaction. If you remember, when we did the section analysis, I developed the PM interaction surface using fiber section discretization in OpenSeas. The idea is, can this plasticity theory be extended to actually model PM interaction for beam column elements? Okay. So, we shall see in the next lecture, and then moving forward we will consider lumped plasticity approach of modeling nonlinear behavior of structures, and from there we will go into distributed plasticity approach. With that, thank you, see you in the next lecture. Okay. Thank you.